Hello and welcome. We begin our system analysis with the simplest type of systems, which are closed and at steady state. As a result, the governing equations simplify considerably. Cycles, which are complicated entities, can be analyzed as closed and steady systems if we are not interested in the details and only interested in overall quantities such as thermal efficiency, Carnot efficiency, etc. So let's go. I've already started a few animations to explain how the governing equations simplify and how they apply to a closed steady system. So here, for instance, the general equations are shown here. As you can see, the mass, energy, and entropy equations are in their most general format. In a closed means all the transport terms go away, and steady means all the unsteady terms, the dE dt, dm dt, and dq ds dt terms go away. So as a result, the equations become very simple. Only heat and external work transfer and entropy transfer and entropy generations are left. So let's see how they apply to a cycle. Here is a concept heat engine which transfers, where heat is transferred from a hot reservoir TH at TH to the heat engine, which is inside a conceptual engine inside the red dashed boundary. Part of the heat is rejected and some net work is produced. And this is the thermal efficiency. Now, similarly, for a refrigeration system, it's also a closed system running at steady state where heat is transferred from a cold reservoir to a warm reservoir and at the expense of net work. In this slide, I'm showing you another animation where is the implementation of a heat engine. This is the ideal Rankine cycle. So even though the boiler, the turbine, and condenser and pump are each open system, look at the red boundary and you will see that across that boundary only heat and work are transferred. That's what makes it a closed system, and it's a steady system because if you take all the guts away from the system, what you see is just steady heat transfer and steady work transfer. Similarly, if you look at the workings of a refrigerator or a heat pump, you will find that across the red boundary there is only heat and work transfer. So therefore, the simplified closed steady equation should apply to a heat engine or a refrigeration system. The test steps that we have for that is under system analysis, closed system, and steady system. This is the one that handles the cycles. Once you click there, you are going to, of course, see video examples of this is a heat engine analysis, this is a refrigeration analysis. So hands-on example page is the default page when you switch to an app. The app is here, very simple app. The default is heat engine. When you click on the refrigerator, you can see the energy and entropy equation as well as the system diagram changes. Same with heat pump. To solve a heat engine problem, maybe the heat supplied is 1000 kilowatt, let's say, to the heat engine, and let's say it produces 500 kilowatt of power. So therefore, we already know the thermal efficiency should be 50%. It's kind of obvious. Thermal efficiency is 50%. And suppose the hot reservoir is at 1500 Kelvin and the cold reservoir is at 300 Kelvin. Let's see what is the Carnot efficiency. It's 80%, obviously, 1 minus Tc over Th, which is given here, the Carnot efficiency. And notice that the entropy generation rate is also found. So where will you find problems involving such simple problems involving heat engine or refrigeration or heat pump cycle? Well, you go to chapter 2 in the problem sections. It has a whole lot of problems involving all kinds of governing equation, mass, energy, and entropy equation, but as they specifically applied to closed steady systems. And finally, in section 5, a number of problems involving overall cycles where the details of the cycles are not so important. When the details become important, we'll have dedicated test steps in the specific branch For instance, we'll follow this open specific system and we'll find vapor power, gas power handled here, refrigeration handled there, and follow the closed specific branch and we'll find internal combustion engines handled there. But if overall analysis is our purpose, this is the simplest route to go, closed steady system.